Hello, good evening. Please do confirm once that I am audible and visible, as well as you can see the slides. Okay. Okay, so let us start. So, good evening, everyone. My name is Ambuj. I am a research scholar here at Agriculture and Food Engineering Department from IIT Kharagpur, and I will be taking a live interactive session for the course Statistical Learning for Reliability Analysis. Okay. So, what we will be doing, we will be going through some of the content which was covered in week 5 in this particular course, that is statistical learning for reliability analysis. And afterwards, we'll be solving some of the questions based on the previous week's content. Okay. And please try to grab a notebook and pen and try to solve the questions along with me. Okay. So, in reliability engineering, shifting from descriptive sampling to inferential parameter estimation represents the transition from observing the historical failure data, which has occurred, to predicting the future system performance. Means historically, the data exists for a known interval, say suppose T0 to time to failure, say suppose T1. So historically, the data exists. But in the due course of time, you have to predict the time to failure in the unknown region. That is, suppose T1 to T2. So in this particular region, if you have to predict that at which particular point, failure will occur, then you have to use this concept of reliability learning. Okay. So, descriptive statistics summarize observed sample behavior, whereas inferential estimation generalizes the sample characteristics to the broader population. This process establishes the stochastic framework required to govern component life cycles and the system reliability, which we want to ascertain in this particular course as well as this particular concept. Okay, whichever we are covering through, they are generally having this particular notion only. Okay, to ensure the reliability of the components through several techniques. Okay, so we want to ensure the reliability. There are three different cores which construct the definitive analytical framework required for this particular analysis. First one is parameter theta, another one is estimator theta head, and the next one is estimate. So parameter theta means a fixed population constant representing a true as well as an unknown characteristic of the entire population. That is, the true failure rate lambda should be known. Okay, maybe it is given with the descriptive lambda, or maybe it is given with the descriptive theta. Okay, so that should be known. Next is estimator. Estimator is your theta head. Okay, a mathematical rule or decision function. Okay, it's a mathematical rule or a decision function. It's only a random variable which is used to approximate the population parameter from the sample data. Okay, we have to estimate the unknown population parameter from the sample data, because you cannot sample the entire population. Okay, cannot perform the statistical analysis as well as testing on the entire population. That is why you are using sample statistics to analyze the population statistics. Okay. So here in this particular case, point estimation provides the numerical basis for calculating the mean time to failure. That is your MTTF. Okay. Determining the plausible parameter values, allowing the engineers to establish baseline longevity metrics, structure of the preventive maintenance schedules, evaluating warranty risk exposure. Okay. So along with this, there is a method of movements, that is MOM. In short, it is written like this, MOM. So the method of movements operates by equating the theoretical population movements to empirical sample movements. Same procedure which we have done in previous lecture for the estimation of population statistics from sample statistics. Okay, so that same topology we are trying to follow. So here you try to see the resulting system of equation yields estimates for the target parameters. MOM is frequently utilized due to its computational simplicity and utility in generating initial values. Yeah, MOM is frequently utilized due to its computational simplicity and utility in generating initial values for iterative numerical solvers. Okay, so this particular method of movements you generally tend to use in case the numerical assumptions are required. Okay, as well as you need to go through several multiple iterations in order to achieve the exact solution. Okay, so that is the case here. Step by step procedure is there. Okay, which we can go through here. Formulate the population movements. First of all, formulation is required. express the k theoretical moment, that is expected value of x to the power k, okay, as a function of unknown parameter theta. Then compute the kth sample moment from observed data. Okay, just have to calculate the kth sample moment from the sample data, that is given like this: 1 upon n summation I equal to 1 to n xis for the entire set k. Okay, then you have to solve the system equations, that is expected value of x to the power k equal to m to the power k, and you need to solve it for theta. Okay, so derivation for the exponential mean also we can present here. For an exponential distribution parameterized by mean lifetime, that is theta, estimation via first movement, that is k equal to 1. Okay, first movement is k equal to 1, second movement is k equal to 2, third movement is k equal to 3. Yeah. Okay, this can be processed like this. Okay, population movement expected of x means the first movement directly is defined like theta. Then the sample movement m1 will be defined like this: x bar 1 upon n summation I equal to 1 to n of entire x size. Okay. Then this MOM estimator for equating the theoretical and sample movements. Okay. That would be nothing, but you directly equate the sample mean to the population mean. Okay. So you will get like this. Okay. It's computationally accessible, yes. MOM estimators lack statistical efficiency. Okay. They can lack, okay, compared to the likelihood estimated based method, because they are always able to extract the exact information. Okay. How much is the likelihood between the population movements and the sample movements? Okay. That we can always go for the estimation. Okay. So likewise for uh, this is regarding to maximum likelihood estimation for the entire data, means entire complete population. Maximum likelihood estimate selects the parameter values that maximize the probability density of observing the collected data sample. Okay. For independent and identically distributed, that is IIDs, random variables x1, x2, xn. Okay, all the random variables from x1 to xn drawn from density f of x over theta, the joint likelihood function. Okay, that is given like this: product I equal to 1 to n f of all the xi's. Okay, over theta. To simplify the uh, to simplify analytical differentiation, the joint probability is transformed into log likelihood functions. Means you take the natural log both the sides and try to compute the entire function. Okay. For case in which you are given the uh, density function as exponential, okay, that is given like this: lambda e to the power minus lambda t. Okay, exponential distribution failure rate lambda is known. Lambda is known, and the function is defined like this. Then directly the construction of likelihood function will be likewise this: y equal to 1 to m. Okay, f of t over lambda. Okay, so both the values directly the function has been defined. So likewise we are trying to compute the product from y equal to 1 to n. Okay, small one. Lambda exponential minus lambda into ti's. Okay, I equal to 1 to 1. Okay. So in case of the product, there are two different terms. The first one is lambda, another one is exponential minus lambda into Tn. Okay. taking lambda outside the bracket, it would be lambda to the power n, directly lambda, lambda, lambda times. Since it's a product, you can take it common outside the bracket. Okay. In case of summation, okay, it would be n into lambda. It would be n into lambda. But in case of product, it is lambda to the power lambda. Okay. So directly you take it outside the braces and then you try to compute this particular product, that is exponential minus lambda into ti product I equal to 1 to n. Okay. So directly what will happen? In case of exponentials, there exists one fundamental property, or in case of exponents, a to the power n multiplied by a to the power n will be equal to a to the power m plus n. Okay. So that we are trying to implement here. Okay. Likely we have gone through the implementation. So similar to that, these entire exponents which we are seeing, they will come in bracket. Okay. That will come in bracket, and you will see something like this exponential minus lambda, okay, outside the braces, and then summation I equal to 1 to all the tables, 1 to n all the tables. Okay. Now you try to formulate the natural log of this particular likelihood. Okay. This particular expansion you can very easily see. If still you have any doubt, feel free to ask me. Okay. Just we have utilized this particular property, exponential a to the power n multiplied by a to the power n, because entire TIs will be coming in product. Okay. So I have taken this particular lambda common and I have said that summation I equal to 1 to n TIs. Nothing much of mathematical nature is there. Okay. That is why it is written like twice this. Now taking natural log here only, both the sides. Okay. So lambda to the power n multiplied by exponential, this particular term is there. Okay. So you need to know the property of logs. Okay. Log base e, a into b will be equal to log base e a plus log base e b. Okay. So likewise you try to compute, and another property is there that log of a to the power m is equal to m log a. Okay. So likewise using both the properties, what we will get, lambda to the power n will be n natural log lambda. Then exponential of this particular term is there. So there is another property that natural log means base is same. Okay, when base is same, what will be your conclusion? That will be equal to 1 only. Okay. So here exponential and this particular term, taking natural log, they will cancel out each other. So entire term will come outside. Here, if m is there, then the answer will be m. Okay. E to the power m is there, and then you are taking the exponential. Okay. You are taking this particular exponential, then the correct option, the correct answer you will get is this, like n. So directly it has come outside the braces using simple logarithmic distribution. So likewise it is defined for an exponential distribution, likewise this. Now setting the first derivative with respect to lambda. Okay, try to differentiate. What you will get? The entire term is natural log lambda minus lambda summation I equal to 1 to n pi. Okay. So differentiate this particular term with respect to lambda, what you will get? N divided by lambda. Okay, natural log lambda. What is the differential of log of x? That is 1 by x. Okay. So directly you will get 1 by lambda, means n by lambda minus differential of lambda with respect to lambda is 1. Okay. So that will come here. Lambda into something was there. So the entire constant term that will appear outside the bracket, and differential of lambda with respect to lambda will be equal to 1 only. So that particular term you equate with respect to 0. Okay. That particular term, if you are keeping with respect to 0, what you will get? You will get you will have to solve it for lambda head as well as theta head. Okay. You will get likewise this particular questions lambda head is n divided by summation I equal to 1 to n ai is and theta head would be nothing but summation I equal to 1 to n ai divided by now some another concepts are there estimation under censoring type 1 and type 2 schemas. You will go through it. In case of your reliability engineering, the data prediction often ends before all the units fail. Okay. So censoring occurs when exit survival times are observed for a subset of test items, necessitating the modified likelihood functions that evaluate both the failed as well as survival units. Basically, it is written right when the entire product in batches. Okay, suppose there are 1,000 products which are getting manufactured in 1 hour. Okay, you have taken a random sample of 50 products. So it is likewise that as soon as we will be testing for the entire 50 products, this batch will be outside for sale. Okay. So with the onset of testing of the products, okay, by taking a simple batch size or sample size, okay, with the onset of this particular process, simultaneously you have to carry it out to update. Okay, so updation of this particular likelihood function you have to carry out. That is what it is written here. Necessitating modified likelihood functions that evaluate both failed as well as surviving rules. So for type 1 censoring or for your type 2 censoring, there are two different cases are there. Okay. In one particular case, the termination trigger is fixed inspection time T. In another case, it is fixed total number of failures, that is R is achieved. Okay. Observed failures in this particular type 1 would be a random variable. In another case, it would be a fixed constant. Okay. Test duration, it's a fixed constant. Here it is a random variable. And similarly, the likelihood function would be directly proportional to this particular terms which you are seeing. Here it would be directly dependent on the total failure rate R. TR would be there. Otherwise, here in case it's dependent on the frequency. So in a type 2 censoring scheme, yeah, maximum likelihood estimation we are deriving for type 2 estimate. Okay. For type 2 censoring scheme, in a type 2 censoring scheme with n number of initial units terminated at rth failure rate, okay, and here the TRs, the failure rates have been defined like this, denote the ordered failure times, okay, remaining n minus r units, okay, survived at least time t small r, exponent r, okay. The exponential the reliability function RT would be defined likewise this. Okay, that is exponential minus T over theta. Okay, so likelihood structure would be defined like this. Okay, factorial n divided by n minus r factorial, then product I equal to 1 to n or 1 to r, 1 over theta e to the power minus ti by theta. Okay. In multiplication with exponential minus tr over theta whole raised to power n minus r. Then you will take the natural log here also, as well as you will differentiate with respect to 0. Afterwards, you will get the entire theta estimate. estimation of this particular theta, theta hat you will get. Okay. So mean lifetime, the estimated mean lifetime equals to the total accumulated test time, that is T total, divided by total number of observed failures, that is R. So that is the deduction which we have made while deriving the MLE under type 2 sensor. Okay. Next is core evaluative properties of your estimators. Estimators are evaluated based on their finite sample and symptotic statistical properties. First of all, there has to be an unbiasedness. Okay. An estimator is unbiased if its expected value equals to the true parameter value. Okay. That is expected of this particular term theta hat shall be equal to theta. Okay. So for a sample mean x bar, okay, that would be expected value of this particular term, entire term 1 upon n summation I equal to 1 to n x size. Okay. So it will come as mu. Okay. It's equal to expected value for x bar you are directly getting it is mu. Okay. So the condition is satisfied here. Then an unbiased estimator is efficient if its variance achieves a Kramer-Rao lower bound. CRLB rule is there. That is this particular rule. That variance of this particular theta hat should be greater than equal to 1 upon I. That is this particular function. So an unbiased estimator attains its lower bound in a minimum variance. Uh, an unbiased estimator attaining this particular lower bound, okay, this one is a minimum variance unbiased estimator for MVU. Then comes the consistency part. An estimator is consistent if it converges, okay, in probability to the true parameter as sample approaches to infinity. Okay. Then there is this sufficiency condition also. Statistic Tx is sufficient. It extracts all the parameters relevant from this data. Sufficiency is verified this particular by this particular Fisher-Neyman factorization theorem. Okay. Then interval estimation, CIs or the confidence intervals. If you would like to plot confidence intervals, equal quantify the point estimate precision by establishing bounds that contain the true population parameter at a specified confidence level, that's 1 minus L. Okay. So normal population mean mu would be there. Okay, known variance should be there. Then the uh, entire, if you would like to derive it via the standard normal distribution, should follow this particular variation sigma over root n. If there is unknown sigma, case one is you are estimating for mu, okay, where variance is unknown. Case two is where variance is not known. Okay, that might be a case. Okay. So for unknown variance, okay, you derive this particular expression. Okay. E x bar plus you are trying to estimate the normal population mean like this particular expression. T alpha by 2, then in minus 1 degrees of freedom, then S over root n. You can also derive it via chi-square distribution. The chi-square distribution also can be used using this particular expression, okay, in order to estimate the population mean mu. Then you try to estimate the exponential mean lifetime, that is theta, under type 2 sensoring using the exact relationship, this particular relationship. The two-sided interval for mean lifetime theta is formulated likewise. This 2 times t total divided by chi square alpha by t and 2r. Then into the range 2 times t total chi square 1 minus alpha by 2 to 2r. Okay. So narrower interval bounds indicate higher estimation precision, enabling refined maintenance scheduling, risk quantification without increasing physical asset probabilities. This particular condition exists. Likewise, we'll try to solve some of the numerical questions based on the previous entire week's content. First one is this one. Okay. Yeah, this is more or less understood to you. Yeah. What is the correct formulation for the log likelihood function, natural log, and lambda? Try to calculate this particular function. A server farm monitors n hard drives. Okay, small and hard drives are being monitored. Assuming a constant failure rate, the time to failure follows an exponential distribution that has been given to you. Lambda exponential e to the power minus lambda t. Okay. So you observe exact failure times. Failure times are t1, t2, tn. Okay. So log likelihood function will like no. What would it would be? You already have derived it. Try to recall it. Yes, then you will see. So you try to see here, we already have computed the function. Okay, it would be likewise this n natural log lambda minus lambda summation I equal to 1 to n. So Ti that I have already computed here. If still have any doubt, feel free to ask me. Okay. See here, n natural log lambda minus lambda into summation I equal to 1 to n T's. Okay. So that was I was asking in this particular problem. So likelihood if a particular function is being given to you, the failure time to failure rate, capital D, it follows an exponential distribution. Okay, and you are observing exact failure times T1 to Tn. Okay. In that particular case only, this particular concept will hold. Okay. In that particular concept only, in that particular case only, this particular concept will hold. Okay. So here the thing is n natural log lambda minus lambda summation I equal to 1 to n Tans. Okay. Likelihood function we will try to estimate likewise this. Okay. So if you are going to simplify and after that you will be achieving result likewise this. This same thing I have explained likewise this. Okay. Here what I did, I just computed the product first of all, computed the likelihood function phi I equal to 1 to n lambda e to the power minus lambda EIs. Okay. Then I took lambda to the power n outside the bracket and then I computed this particular function. Then I took log, natural log both the sides and then I got this particular result. That is what the explanation has been written. Whenever you are taking log or natural log, because the physical maximum of a function occurs at the same point as the maximum of its logarithm. Okay. So in reliability engineering, multiplying thousands of tiny probabilities causes the computer underflow or overflow, whatever you can call. The log transforms a massive multiplication problem into a simple addition problem, okay, thus allowing for easier solving of this particular equation. Lambda with equal to n over summation theorems. Okay. Next is method of movement. Okay, this particular question is there. You are evaluating the tensile strength of a new composite material. It follows a normal distribution and with variance with mean mu and variance sigma square. Okay, we need to estimate the population variance sigma square using method of movement. Okay. Here M1, which of the following is the correct M1 or method of movement? Okay. For estimator for sigma square, where M1 has been given likewise this 1 upon n summation I equal to 1 to n exercise, then M2 is 1 upon n summation xi square. Okay. So likewise you try to complete both M1 and M2 and try to deduce what shall be your estimate about sigma square. So you try to see here first moment if you try to conclude it would be mu. Okay. That will be coming as L1. Second is expected value of x square. Okay, that is variance of x plus expected value whole square. So that is sigma square plus mu square. Sigma square plus mu square is your n2. Then you substitute for mu, right? Okay, you will get sigma head square plus sigma square equal to m2. You try to estimate sigma head square from here. You will get m2 minus m1 square. Correct option would be D. Next question, we'll try to go through it. Okay. This particular one, that,
Sir, the
yeah,
previous question, we are using proportional. We want to find the variation between
I
S1
think
square.
you are not audible at all. Sorry, you are not audible at all. Either you try to change your mic or you try
Okay.
to, yeah, yeah, speak.
The previous question answer is
Yeah,
if you want to find the variation between two things, the proportion test we need to F test we need to do. That is F1 square by F2 square. Then it is divided. There we are doing divided to find out the things. Same thing sir, here also.
still I'm not able to hear your question. You are talking about something about F test that I got to know. Please write it down in the chat. Or,
See, F
yeah,
test we are doing, sir.
yeah, yeah,
F test we are doing for find out the variation between two different things.
yes,
Correct na? Same process here also applicable na sir. There we are doing S1 square by S2 square like that. But here we are doing minus
yes,
M1 minus M2 square.
yes, yes. Reduction of analogy is correct. No problem. You can reduce that right.
But
So,
we are using here different methodology. That what I'm not understand.
yeah, here we are not using it entirely. We are not copying it entirely. We are trying to deduce it from the basic equations which you have already used. Okay. So, where exactly is the doubt? Please elaborate. Means what exactly is the doubt? Where exactly you find problem?
So, but methodology itself changed sir. I have test to this one.
Okay, okay, okay. I'll try to re-explain it. Okay, no problem. I'll try to repeat it once again. Meanwhile, you just try to solve this particular problem. You are testing n equal to 100 aerospace bearings to save money. Testing strictly ends at the critical value TC equal to 500 hours. Exactly R equal to 15 bearings fail before 500 hours. Okay. The remaining 85 survive. What is the core likelihood function structure capital L for this type 1 sensor data? Already the derivation part we have seen. Okay. Just have to tick the correct option. Likewise, correct option would be A only. Okay, this we already tried to derive. Okay, so the for a field R items, okay, R number of items, smaller field number of items, we know the exact number of times means from 1 to R, the entire function has to be in product. Okay, so for the n to R survivors, the R number of survivors, we only know that they live past the critical time Tc. So this particular probability that capital T is greater than Tc is 1 minus small capital F Tc. Okay. So this particular probability would be directly proportional. Okay. If you try to assume the independence, this particular RTC raised to power entire raised to power n minus R and this particular property. So this we try to see. Okay, if you see try to have a physical significance. Okay, we only calculated the likelihood for 15 number of failures. We would artificially inflate the failure rate. We must give the component credit for 85 units that survived. Okay, multiplying the reliability function RTC mathematically factors this particular silence in the of the surviving ones. Okay. So that is why we are trying to add this particular inflation factor. Okay, trying to inflate the actual survivors. Okay, so that is the concept here. Next is this particular question related to type 2 sensoring. Okay. You test n equal to 50 mechanical switches, decide to stop the test the exact moment the 10th failure occurs. R is equal to 10. The test ends at times t smaller. Okay, at this particular time t smaller. Assuming an exponential distribution small f of t equal to lambda exponential e to the power minus lambda t. What is the MLE mean time to failure under type 2 sensor? Yeah. So MTTF, they will try to calculate. Okay, how we will calculate. Already we have seen in the lecture right now.
Sir, sir, one thing, sir.
Yeah,
This all, this all things are related to the hypothesis, sir.
no, this is not. This part comes after hypothesis test.
Sir, this week fully we learned what is hypothesis, sir.
Yes, you learned what is hypothesis only.
Yeah, madam, that only not told that we fully the classes everything. We are we learned just basics from
Okay,
hypothesis.
okay,
It is all our high level questions which we cannot expect.
okay, okay. I will see to it next time. I will formulate the questions accordingly. Let me give a check. But I explained you the entire thing in entirety.
Yeah, we
Here
explained.
I try to explain you the entire MLE part and every other part. Okay, if such thing is there, from the next time I will try to make the slides accordingly. Okay,
Why? Because we are very studies very poor, sir. So that's why.
okay, okay. Okay.
population, definitely we have hypothesis collapse, that is selected even what is alpha. Tell this.
Yeah. Okay, I understood your point. From the next week onwards, I'll try to take a note of it. I'll not explain these concepts. Okay, the concepts which are beyond the your lecture printouts, I'll not explain those. Okay, I'll take a note of it. I'll try to restrict myself to this particular distributions. Okay, no problem. Okay. So if hypothesis testing is there, then we'll formulate the MCQs and the handout accordingly. So most of the thing in shortly up to the entire syllabus I think I've covered. The regression part is remaining. So accordingly I will adjust. And Nova I think we have covered. Statistical inference already covered. Confidence interval. Okay, that is the part for next lecture. It is there in the syllabus, whichever I am talking about, but it is in the next week's
Thing
syllabus.
of that sort.
Okay.
How I'm reframing
Okay. No problem.
it?
The entire thing which I am covering today is it is there. Okay. It's there, but it is there in week 6. Sorry about that. It is there. You won't be having any trouble. Okay. Sorry about that. It is there, but it is there in week number 6. Now I can see it very clearly here. Okay. No problem. In the from the next week onwards, I'll try to formulate the questions as well as the handouts accordingly. It got mixed, a little bit mismatch was there. So no problem. You just try to see this particular hangout. It will help you in week number 6. Okay. It will greatly help you in week number 6. It got mismatched with week number 5. Till week number 5, that I can see here that hypothesis testing is already only done. So I'll formulate from next week onwards. You won't be facing this particular issue that I am ahead of what madam is teaching. Okay. But no problem. In this week only, whatever things I have just covered here, they would be in week number 6. So mean time to failure in this particular case would be defined like this: I equal to 1 to r ti is plus n minus r tr divided by r. This would be defined likewise this. Okay. This would be definitely derived. Okay. It's derived also, and I have also tried to derive along with this. First of all, I have defined the log likelihood function, then taken the natural log, then differentiate with respect to lambda, put it at 0, then find out the mean time to failure. I got it as 1 upon lambda. And okay, that is what I got. So B would be the correct choice. Next, you try to define the maximum likelihood estimator to calculate the variance of a test data set like this. Okay. Sigma square MLE, that is maximum likelihood estimator, as 1 upon n summation x I equal to 1 to n xi minus x bar whole square. Okay. You are trying to estimate the population mean mu with the help of the sample mean x bar. Okay, if the estimator is unbiased, is this estimator unbiased? First of all, you have to determine. If not, then what is the expected value of this particular expected of sigma square MLE? Okay, so the correct option would be it would be a biased estimator. Okay, why I am just saying it as biased? Because first of all, I am calculating this particular expected value. 1 upon n summation xi minus x bar whole square. Okay, you are trying to calculate this, and this is dependent on the original term sigma square. Okay, as well as the number of samples which you have taken. Okay, so that is why it's a bias estimator. Okay, the maximum likelihood estimator underestimates the true population variance. Why? Because the data points will always be physically closer to their sample mean x bar than to the true population mean mu. You have to apply Bessel's correction. This one term is known as Bessel's correction. Okay. Divide ding by n minus 1 instead of n to fix this particular deviation which we have observed. Okay. Then the unbiasedness should be observed, means the estimator centers perfectly on the true target. Okay, expected value should be 0. Okay, that is the first requirement. Consistency should be maintained. Sample size, and as it would be approaching to infinity, the estimate perfectly converges to the true value. That should be the concept. Efficiency should be there. Okay, variance should be in a tightest possible variance. Okay, it should be there. Means estimator should have a very it should be reaching to the Kramer lower bound limit. Okay, we have already seen. Then the estimator extracts 100% of the useful information from the sample. Okay. Now, regarding to the confidence intervals, here in this particular question, you try to see, you estimate, you measure the capacitance of n equal to 12 capacitors. Okay. A small sample, the true population variance, sigma square is unknown. You want to construct a 95% confidence interval for the true mean mu, and which pivot statistic you will try to use, because the sigma square is unknown. Okay, the population variance is unknown, so you'll go with t test. Okay, x bar minus mu whole divided by s over root of n. Okay, this we have just seen. Okay. This we just have seen here. Where after this, after this, after this. This limit we have seen, here we have seen unknown variances there, and what are the test statistic? We have just seen it. Okay. So sigma is unknown. You substitute for the sample standard deviation s, then the variable x bar minus mu whole divided by s over root of n no longer follows a perfectly normal distribution due to added uncertainty. So you would be getting this particular interval. Okay, we have already seen it. Then, in case of your chi-square distribution, okay, chi-square distribution already we have just seen n minus 1 s square over chi-square alpha by 2 in minus 1 to 1 minus alpha by 2 n minus 1. Whole term will remain as it is. So, likewise, in quality control, variance is often more important than the mean. Okay, you need a 1 minus alpha confidence interval for the variance sigma square of the voltage regulators, because of the chi-square distribution is not symmetric like this. The interval is constructed using two different critical values. What is the correct CI formula? Means confidence interval formula directly we are being asked. So that would be nothing but your option number A. We have just seen it. Okay. Next is, unlike the normal distribution, variance cannot be negative. Okay. Physical derivation you can just try to see here. Okay. So the chi-square curve is squashed to left at 0 and has a long tail on the right. Therefore, we can't just write plus or minus. Okay. We have to divide it by two distinct critical values to accurately capture the middle of the 95% interval. So that is defined likewise this. Okay, and you have to just keep the sigma square bounded to these two particular values. That is n minus 1 s square divided by chi square alpha by 2 to n minus 1 s square divided by chi square 1 minus alpha by 2. Okay. Then this particular question is there. you are analyzing a failure rate lambda of cooling pumps. Okay, the data follows an exponential distribution. Known statistical theorem states that for exponential data, 2 lambda n x bar, okay, follows a chi-square distribution with 2n degrees of freedom. Then what is the exact confidence interval? Okay, so exact confidence interval directly you can calculate. Okay, it would be coming in option number A. Okay, because this 2n you have to take outside. Okay, so physical explanation is like, why is this? This is the powerful shortcut in reliability engineering because the sum of exponential variables is a gamma distribution, and the gamma distribution is mathematically related to your chi-square distribution. You can generate perfectly exact confidence intervals without relying on the simple limit theorem. Okay, we already have seen it. So this particular option will hold in this particular case also. Okay. This is somewhat advanced. I thought of explaining it. Okay. And this particular thing was regarding the lecture. You would be seeing all of this, the content. Okay. Most likely in your week 6. Sorry about that, that I am a bit ahead. Okay. And the question which you asked, I will just try to explain it once again. Okay. Method of movements. Okay, method of movement concept. I will just try to explain it once again. Give me some time. If you have any doubt regarding hypothesis testing, feel free to ask me. Okay. Whatever content has been covered, if you are having any doubt anywhere, if some distribution is not clear to you, or there is a doubt in null hypothesis, alternate hypothesis, formulation of the hypothesis, or any doubt in general is there, feel free to ask me. Okay. The entire chi-square distribution and the limit theorem, the which I just covered, it is there in week number 6. Likewise, I'll try to give you a glimpse of this particular method of movements. You'll have a better idea. see here the method of movement, MOM method. Okay, it's one of the foundational as well as most widely used technique. Okay. It's a foundational technique in case of your point estimation. Okay. Core principle relies on the law of large numbers equating your theoretical population to your empirical sample movements. Okay. Theoretical population equating to the sample movements in order to solve the distribution parameters. Okay. Theoretical versus sample movements. Okay. Likewise, if you will try to take them, okay, so exactly it has been defined in a good formal manner that I'm saying. Yeah, theoretical versus sample movements. If you will try to see, okay, for a random variable x, the kth raw population movement is defined likewise this. Okay, mu k is expected value of x to the power k, where k, the corresponding kth raw sample movement can be calculated from the observations. Likewise, this. Okay, so if the your distribution that is following normal distribution with variance mu and standard deviation sigma square, okay, then you can calculate likewise this. Okay. To estimate the population mean mu and the variance sigma square for a mean tensile strength, if it is following at all, and with variance mu and with mean mu and variance sigma square, you try to calculate the first movement. The first movement is defined likewise this. Okay. Expected value of x. Okay. That would be nothing but 1 upon n summation I equal to 1 to n x i's whole to the power 1. Okay, so it will come as nothing but population mean mu. Okay, so first movement would be m1. Now you try to calculate the second movement. Second movement would be defined likewise this expected value x whole square. Okay, so for calculating this, you need to use the variance identity. That is, variance of x is nothing but equal to expected value of x square minus expected value of x whole square. Already you have seen it. Okay, you just try to rearrange it. Then you try to calculate expected value of x square. Means the second moment you will try to calculate that would be coming as variance of x, that is sigma square, plus expected value of x, that is already calculated mu whole square. Okay, compute it to M2. Okay, that was given in this particular question. Okay, M2 would be nothing but M2 already you have calculated it as sigma square plus mu square. Okay, sigma square plus mu square. Okay, and M1 already it is known to you, that is mu. Okay, now you have to calculate for sigma square. Okay, sigma square you try to calculate. Just nothing. You rearrange the terms like this. It's sigma square. M2 is nothing but sigma square plus M1 square. Okay, plus M1 whole square. Okay. So likewise, sigma square will be nothing but M2 minus M1 square. That was being asked in the question. Don't worry, this entire thing as well as the derivation of the entire movements that would be done in the upcoming. The expression m2 minus m1 square is algebraically equivalent to this particular expression, which represents the sample variance computed with a divisor n. And for a normal distribution, this MOM estimator coincides exactly with maximum likelihood estimator. It is consistent and asymptotically unbiased though biased for finite sample sizing is small n compared to the sample variance s square. So entire description once again the thing is there. You can see here, as well as I tried to derive it for gamma distribution also. Gamma distribution will alpha and beta as the parameters, shape parameter alpha and rate parameter beta. Don't worry, this entire thing would be covered in the coming lecture. Regarding hypothesis testing, if you have any doubts, feel free to ask me. Okay.
Sir, we are taking significance level now, sir. 5%, 1%, 10%.
Yeah,
Yes, that means we are accepting the alpha 5%
yeah,
type 1 error.
yeah,
That is, that means 95% we are not accepting.
yeah. It's somewhat like this.
Somewhat like that.
Okay.
Okay, so now we are going to prove
Mhm.
we are accepting 5%, whether it is follows that is or not. We are going to prove by h1 h naught is equal to mu is equal to something,
Yeah,
or h naught is h1 is mu greater than or something is equal to something.
yeah, yeah, yeah. That we are trying to prove. Yes.
By using different types of
Uh-huh.
distributions.
Uh-huh.
That means suppose we you explain the chi-square distribution, t
Nice.
distribution, z
Yes.
distribution.
Yeah.
Based on that, all studies you are going to prove that thing.
Yeah, I am going to prove that either I am accepting the null hypothesis or rejecting the alternate hypothesis or vice versa. So that
Yes,
particular conclusion I am basing on the particular test statistic. Okay. I'm calculating the test statistic. I'm just trying to uh, compare it with the standard distribution value, and based on my conclusion of what the exactly test statistic, whether it is greater or less than the standard value, I'm either accepting the null hypothesis, rejecting the alternate hypothesis, or converse of this particular step. Yes.
yes. Now it is clear, sir. This is the first point of level. But
Okay.
basically, H naught we are taking as a null hypothesis.
Yeah, yeah.
Based on what criteria we will take, it is based on Madam is taking based on the question what is asking. Based on that we will take in there. But
Yeah.
each question to question is changing actually.
Yeah, question to question it will change actually, because the null hypothesis formulation is the question statement only. That there is exists
Questions.
no difference between the population mean and the sample mean. Okay, that is the statement of the null hypothesis. Alternate would be there exists significant difference between the population mean and the sample mean. Yeah, yeah, yeah. You told tell what you want to tell.
Madam first time taking the first decision.
First decision.
And that means in a question, first decision is taking mu h naught is equal to mu is equal to some 500. If you see
Okay,
second question, h
okay.
naught is equal to some h naught is equal to 8. So
Uh-huh.
it is something making me difference how we can take a null hypothesis.
Okay.
That means it is based on our predictions. I think
Is based on what predictions.
not our predictions, but
You are able to see now what I am presenting. This
yes, yes, yes,
particular
yes, yes.
PPT you are
Same
having.
presentation.
Same
Yes, yes,
presentation.
yes,
Yeah, yeah, I
yes,
have
yes, yes.
access to it. So in whichever slide you are having a problem, feel free to ask me. I am here to improve. So this would be clear. The problem is in the hypothesis testing. I'll move it to. So suppose this particular question is there. Okay, hypothesis. Shall I start from here, or you are having any specific problem in which you are having doubt? I'll explain each of the problems so it would be more clear to you. You want me
It's
to
the first.
use? Uh-huh.
That is
Speak, speak,
that the
speak.
first problem only.
Okay, okay. That first problem only. Okay. I'll go
Yes, sir.
through. I'll keep on going through all the problems, so you will have a better idea, right? Will it work for
Yes, sir.
you?
Yes.
Okay,
That is a box question. Is
okay, okay. I'll walk you out through all these problems. No problem with it. Are you having access to this particular PPT or PDF?
Yes. I am also open, sir.
Oh, okay. Then
Yes, you opened the correct question only, sir. That is
it's there. Okay,
basic level.
this is case study 1. You want me to explain case study 3?
This case study, I understand that.
This you understood?
Sir, what is the meaning of,
Uh-huh.
sir, again, it is getting out exclusive and exhaustive. You already explained in previous class itself.
What is the difference between X?
Exclusive and exhaustive.
Oh, exclusive and exhaustive. Oh,
You already explained it, but here it is coming difference meaning.
okay. Two different terms are there. One is exclusive, another one is exhaustive. So you are having doubt in this. Okay, I will try to clarify. But first of all, I'll have to frame an example that would be better, right?
Yes, sir. Yes, sir.
See, one term is exclusive. Exclusive generally it means that two or more events they happen or exist at the same time. Exhaustive means a set of options. It covers all the outcomes out of which at least one has to occur. For a simple example, if you are tossing a coin, it can lead on head or tail, but not both at the same time. So these are exclusive events, means events which cannot happen together. If one will happen, the other will not happen. Okay. There is no shared overlap or shared space or overlap between them. Okay. This is regarding your mutually exclusive events. While you try to see here, mutually exhaustive events are there. Mutually exhaustive events are there. So what exactly it means? Means a group of events which cover every single possible outcome. Okay. So together they make up the entire space of possibilities. Okay. Entire sample space that is getting covered. Okay. So suppose you are rolling a standard die. Okay. So that is having six different sides. One, two, three, four, five, six. Okay. So the numbers which are there, they are defined in a set like this. One, two, three, four, 5, 6. Okay. So it means this particular set is having all possible outcomes. Okay. So this particular numbers, the set of this particular numbers are mutually exhaustive. Are collectively exhaustive, not mutually. These are collectively exhaustive. Means they are exhaustive because they are having every possible result. Okay. So exhaustive, you try to remember like this when you are exhausted. Exhausted means your energy level is down. Means you have searched for every possibility. Okay. So it's generally related to a set which is having every possible outcome. Okay. And exclusive means whenever one event is happening, another one cannot. Okay. Means if you are flipping a coin, then either you will get head or you will get tail. There is no possibility that you will get Head and tail, either of head and tail or both at the same time. None of that makes sense. Okay. So this is regarding mutually exclusive and collectively exhaustive. Okay.
That means exclusive means it is a two-tailed test.
Yeah, it's a two-tailed test. Yeah,
Exhausted means it is a one-tailed test which is greater than or less than or equal to, or greater than or equal to.
yeah, absolutely. Okay.
So, yeah, got it, sir. Sir, everywhere we are taking alpha value only, alpha significance only. Based
Uh,
on that, we are calculating the things.
yeah,
But we are not. We are considering only type one error. But type two error we can't able to consider. That means beta. What you open calculating with beta.
yeah, yeah,
What is the importance of that? We are not considering this actually while calculating while doing testing.
yeah, yeah, yeah. We are generally eliminating the influence of this particular beta. Now you want to know why, right?
Yes, slowly with little knowledge, sir. Not that much depth. If you open Parma, we can't remember it.
So I'll try to explain in simple words. That is what we want to say.
Yes, sir.
So type 2 error, it generally happens when a statistical test fails to reject a false null hypothesis. Okay. It means it's a false negative. Means the test misses the real effect or the real difference. Okay. Type 2 error is generally denoted by beta. You must be knowing it. It is the exact chance that your test will fail to find an effect when an effect actually exists. Okay. So statistically, it is equal to 1 minus beta. Okay. If a relation is given to you, the exact power is the correct chance of finding a real effect. If beta this in the here the particular problem is 0.20, then there is a 20% chance of a type 2 error. So the power becomes 80%. That is 1 minus beta, statistical power. Common causes of this particular error are small sample size, not looking at enough data makes it hard to see a real pattern. High variability is there, too much noise is there. Strict alpha level is there, means setting a very low significance alpha makes it harder to detect the results. Small effect size is there. How you can reduce this particular error by increasing the sample size, raising the value of alpha, changing the significance level from 0.01 to 0.05. It will raise your risk of type 1 error, but at the same time, the type 2 error will get reduced. Okay. So you are asking it why we are not considering every time type 2 error. First of all, at your level, you should think that it is generally given in the question whether you have to give consider the type 1 error or type 2 error. Why is it excluded or it is not generally considered? Because it is very negative. That is answer in simplest terms. If you want in-depth explanation, I can provide you that also, and I can derive it why it is very less. Okay, clear? Not clear?
Yeah.
Clear?
That is got it. No need to discuss about beta. We will discuss about alpha only. You are telling. Then we will get conclusion
Hmm, hmm,
based on the alpha at
hmm,
0.05 significance level.
hmm. Exactly. It is generally neglected or it is overlooked because we generally want to focus on your alpha. Because type 1 error is the most profound type of error. Okay. Standard testing controls the false positive strictly, so treating a null hypothesis is the default safe position. In short, it is the conclusion is that only that it is negligible. Within standard experimental procedures, if you are repeating the experiments, then it would be negligible. That is why we are just sticking with type 1 error in general.
Oh,
But if you go in depth and profound statistics you want to apply and you want to increase the proficiency level, definitely you can consider the experiments.
mm, not required, sir.
Okay.
Sir, case to study once of sir.
Okay.
Which in testing.
Case to study. Which page?
Page number 67, sir.
67.
Slide number 67.
Slide 67. Slide number
Yes,
67 is this. Yeah.
correct, sir. This only.
Yeah.
Sir, we
Consider
take
the
an H notice.
yeah. You tell first. You tell first. Yeah.
Okay. Here everything is clear, but slide number 72,
Mhm.
based on what we taken, sir, x bar is equal to less, mu is equal to 8 we taken. Come on.
Mhm.
Yes, this one, sir.
Mhm.
Here, suppose the null hypothesis is to be rejected if the mean value is less than 7.9 or greater than 8.1.
Mhm.
This is how you're telling, sir, based on the question. I am not getting this point.
Yeah. So here, what exactly is the problem? How the 7.9 and 8.1 has come?
The given standard deviation is 2
Uh-huh.
based on 0.2, not 2.
Uh-huh.
But if it is beyond that standard deviation, means it is rejected.
Yeah. If it is beyond the standard deviation, it is rejected. Yes.
Yes, you're telling that. But is asking whether mu is equal to 8 or not.
No, no, no.
Is question that only, sir.
No, 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 sir. You got it wrong, sir. Sorry, sir.
Sir,
Sorry, sir.
trying to learn.
Sorry, sir. Terrible
Medicine
sorry, sir.
production company packages.
I'll explain you this. Same time problem you wanted to fix. Just give me a moment. I'll explain it in my own language. Just give me a moment. No problem. Keep on asking. But what inference you made, it was not correct. That I can assure you. But you will come to know the correct inference. No problem.
Sir, got it, sir. It is in between that p-value alpha values falling in between that two criteria means it is acceptable. If it is not falling in between that value means it is not accepted. That is okay, but question is asking in such a way. whether the data is follows mu is equal to 8 or not.
Hmm.
But how you consider that sigma value 0.2? That means the guy already given sigma value, so that's why we consider whether the values falls in between means we are accepting that thing.
Yeah, that would be provided to you. That has not to be just taken into consideration. Just give me a moment. I am also trying to see. Problem has been different, I think, than sigma less breakdown. This particular statement is with the question. The given the sigma, the standard deviation of the sample is required. Means sample standard deviation would be given with the problem. Means here only at this particular place only where the problem is defined. Here it has been mentioned. You take it for granted that sigma has been mentioned at 0.2. Now you don't have to do anything. You formulate it like a hypothesis testing problem. Okay. Suppose X is the amount of medicine in a tube in ml, then you try to formulate like this. The machine is supposed to fill each tube with 8 ml. Null hypothesis would be mu is equal to 8 ml. H1 would be alternate hypothesis, mu is not equal to 8. Okay. So since the sample of n equal to 16 tubes is taken, appropriate test will depend whether sigma is known or whether sigma is not known. Okay. If the sigma is known, which is there in this particular case, means sigma is 0.2, then you use go for one simple z test. Okay. That is x bar minus mu 0 divided by sigma over root n. Okay. Mu 0 is 8, n is 16. Okay. Z you value you try to calculate. That is nothing but you try to calculate it as alpha equal to 0.05. If you will try to calculate very easily you will be able to achieve the conclusion. If it is not known, you go for t-test. So with the understanding of slides, it becomes somewhat hazy because one slide after another slide, some data is given. But in the problem, at the very first line, it would be declared whether sigma is known. If sigma is known, you go for z-test. Sigma is not known, you go for t-test. Okay. Still, any doubt is there, or is it clear?
Yeah, I got it. So that point.
Oh, yeah. Any more thing?
Sir, p
Anywhere you
value,
are?
sir.
P-value. Slide number
Slide number 53,
53.
page number 204.
Two knots. This
Yes,
P,
sir.
the P-value
Yes,
is
sir.
the probability of committing a type 1 error if the actual sample value of statistic is used as the boundary of the rejection reason. Yeah. So where exactly is the problem?
That the statement itself somewhat confusing, sir.
Okay. You want to understand that what is this P-value? Oh, that's good.
Yes, sir.
See, you try to understand. Uh, type 1 error is generally a false positive. Okay. It happens when you reject a true null hypothesis, including an effect or a difference which exists when it does not. The exact p-value is your data's probability showing showing results as extreme as yours by a random chance alone. Okay. So you compare this p-value to a set error rate, which is your alpha, in order to decide if the results are significant. Okay. Type 1 error, you can, in simple terms, you can define it like a finding a fake effect. Okay. In real world scenarios, for example, a medical test says a patient is sick, okay, but the patient is actually healthy. It is corresponding to type 1 error. Okay. Alpha is the maximum risk which you are taking to accept type 1 error. It is generally set at 5%. Suppose 0.05 or 5%. Then what is this p value? P value is, by definition, it is the odds that your results happen purely by luck. Okay. If your p value is lower than your alpha value, suppose p is less than 5% or 0.05, you will be rejecting the null hypothesis. Okay. P value is not the exact chance that a type 1 error occurred or that your result is false. If it is given to you in the question, you have to use it. Okay. You can use alpha also to limit the type 1 errors before you are exactly starting. If alpha is 0.05, you accept a 5% long-term chance of false positive. Okay. If P is less than alpha, you claim a discovery that knowing you run that a small controlled risk of type 1 error exists. Okay. So alpha is more important in real case scenarios. P value is by definition the odds that your test results happen purely by luck. And by comparison of your P and alpha values, you are in a position to say that whether I am able to uh, accept my type 1 error, or you are not including your type 1 error in the scenario, in your test hypothesis. That is the case. Okay.
So that means you're telling me
Mhm.
alpha, if your alpha value is less than 0.05,
Mhm.
sorry, less than 5%
Mhm.
p value,
Mhm.
then we need to reject null hypothesis.
Yeah.
If it is
Yeah.
greater than means we need to accept null hypothesis. That
Yeah.
is the
Yeah.
statement.
That is the statement. See here, it is already written. P value is the probability of committing a type 1 error if the actual sample value of statistic is used as the boundary of the rejection region. Interpreted as the
But
indicator. Yeah, yeah, yeah.
how to calculate that p value, sir?
That would be given in the question. P value don't have to calculate. That would be given in the question. In statistics, only the inferences we have to make. Okay. The analyst provides the p-value and the decision maker determines the significance level based on the cost of making type 1 error. See, analyst will provide you the p-value. Now you have to make this particular decision, that whether p is less than alpha, p is greater than alpha, whether you are accepting the null hypothesis or rejecting the null hypothesis. You are committing type 1 error, you are not committing type 1 error. That's only you have to decide. Okay, clear?
Okay, okay. That means H naught is that means how we need to write means H naught is equal to null hypothesis is equal to P of mu is equal to 0.
No, not like this. P of
That
mu.
means H.
Uh-huh.
That means we are accepting the probability of mu value. That means
Yeah.
any example.
Mhm. In any example, you are correct. If P is less than alpha, then what you claim a discovery that you are running. a small controlled risk, which is alpha, of committing a type 1 error. That is what your statement should be.
Okay. Okay.
Statement should be framed likewise this, because these are standard statistical methods. Statement you have to make like this. Okay. I'll repeat, p value by definition means the odds that your results happen purely by luck. If your p value is lower than your alpha value, you reject the null hypothesis. P value is not the exact chance that a type 1 error occurred or your result is false. Okay. These points you try to remember. Okay. Now, setting the alpha, setting the p is in the hands of the experiment, who is experimenting and who is making conclusions. You use alpha to limit type 1 errors before you just even start. Okay. Alpha is 0.05. You accept that a 5% long-term chance of false positive would be there. When your p is less than alpha, you are claiming a discovery, and you are making a statement that knowing that you run the small control risk, there will be a existence of type 1 error in the experimentation. That is the thing. Okay.
Okay, sir. Now,
Uh-huh.
while we are doing this type of test,
Uh-huh.
chi-square test, t test, and
Uh-huh.
some last
Uh-huh.
class what we discussed, the tests only we need to use here. Any
Yeah,
other
yeah,
tests is there?
yeah, yeah.
Jet test, t test,
That will
parametrics.
be that entire table along with where which that particular test is applicable that I have given to you. Go through it. Okay. And the decision which test has to be applied, that will you will be able to achieve it when you will be solving multiple problems. Okay. Then only you will be getting idea that which particular test has to be applied. Okay.
Sir, any trick is there, sir?
No, trick is not good. Go through the notes there. I have made it clear. Then which particular case scenarios are there, right? Particular keyword would be there mentioned in the question. Based on that only you were able to formulate the distribution as well as which particular test of statistic you have to apply. That,
This all
yeah, yeah, yeah. This all.
this all are confusing, sir. But jet square, jet
With
test is also same t test. X bar minus mu by sigma is equal to is a jet test. T test is x bar minus mu by s by sigma square is equal to t test. And the chi square is n minus 1 s square by sigma is chi square. Then f means
no confusion is there. You give it some time, try to practice. Try to chew food piece by piece. That will eliminate all your doubts. Okay. Very simple and very effectively here it has been explained to you. From the next session, I'll explain you this only. I think I need not to make any separate PPT. That would be more than sufficient. I'll explain you this once again. Your concept will be clear. Meanwhile, I'll prepare some of 5, 6 problems that I will give you. Right? It will work for you better, right? Instead of me
correct,
explaining
sir.
some of the problems. Correct, right?
Yeah, your advanced level explaining, sir, that we
Okay,
can't able
okay.
to catch.
Okay. That I will not do. I'll explain this only. And with this, I'll prepare some of the problems. They will be somewhat advanced, so you will get better idea. Mixed type of problems. I will not bring my separate PPT into the notion. Okay, that will work for you. Okay. And similarly, if any doubt is there anywhere, you can ask. Okay. But by the end,
Sir,
clear
power,
all your doubts. Yeah, yeah.
what is the power concept, sir? That is, madam.
What is the power concept? Explained in detail, somewhat prior to power concept, somewhat later to prior power concept. Power BI is there, which currently I am aware of.
Practical material.
Power of a generally statistical test is the chance that the test will correctly reject a false hypothesis. It will try to measure how well your test can find a real effect or difference when one truly exists. You can write it down as 1 minus beta. Beta is the risk of committing type 2 error, missing a real effect. Got it right? Shall I repeat once again? If you want to jot it down, you can jot it down. Power of a statistical test. It is the chance that the test will correctly reject a false null hypothesis. It,
Yeah, correct,
measure,
sir.
it measures how well a particular test can find a real effect or difference when one truly exists. How well a test can find a real effect or a difference when one truly exists. It is written by 1 minus beta. The power of a test is 1 minus beta. Beta is the risk of committing type 2 error or missing a real error.
Sir, okay, sir. How we can relate this concept to reliability, sir?
See, everything which we are conducting, see, the flow I tried to explain you, right? I'll explain it once again. Suppose a particular assembly line is there. Okay, it is producing 1000 number of products. Okay, so for manufacturing this 1000 number of products in 1 hour duration, there are capital N number of components required. Okay, so for solving for uh, manufacturing this 1000 number of components, say supposedly you have to operate the machine 24 into 7. The condition is like this. So either your components can be connected in parallel in series. Okay. So the reliability is that particular concept in which we are trying to demarcate that how long our entire assembly line can function correct without needing a repair. Okay, this is regarding reliability. Now, for ascertaining reliability along with the quality of the products which are getting manufactured, we are going for this test of statistics. Okay, we individually cannot test these entire 1000 products, so we are taking a sample of suppose 50 number of products. Okay, and we are checking their particular quality. Okay, and on the basis of our quality test of this 50 sample size, we are ascertaining whether this entire batch can go into a market or not. So this entire thing is related with the manufacturing rule. Okay, reliability. First of all, we ascertain it. Then we are going for testing the products. And in general, we want to maintain the quality of the products which are coming out of the market. So slowly and gradually, we are moving one ladder at a time. Okay, got
Yeah,
it?
sir, got it, sir. But how we can say this conclusion to top management? That means they want systematically and theoretically the solutions finally.
The solution is dependent on the problem which you have found out. First of all, understand it. In the entire management team would be there. So a particular role will be designated to you. If your role is of the quality manager, okay, then your certain roles would be provided to you. The responsibilities would be provided to you. Okay. So the general things you have to convey like regular maintenance is required, regular checking of the operation is required, regular testing is required. That you can tell to the management. On a daily basis, you have to keep the samples. Depends on the industry in which you are working. Okay, how long you have to keep the samples. And continuously you have to test for the errors. That is what you can convey to the management in general. But if you are working in a specific industry, then tell me, I'll give you the specific codes which you can convert or specific tests of significance which you can apply. Yeah.
Is okay. We are belongs to the manufacturing industry, sir,
Okay.
and I am the I am the quality assistant manager.
Okay. Okay.
I I try to learn this all this after a long time. So that's
Okay.
why I want to use this type of methodologies, the hypothesis testing. But this is giving conjecture. That means it is not giving the exact solution, but it will give the uh, this hypothesis testing. It is giving this all test the probability of getting chance. That's all.
It will, the statistics can give you probability only. It cannot give you the exact solution. Exact solution, if it is engineering, then contact that particular team, R&D team. If it is related to the quality of the products that is getting manufactured, how exactly at which particular steps, n number of steps would be there. You to list out all of those steps. At which particular step the quality is getting degraded that you have to find out, and then you have to convert. So this particular portion is not able to function properly. It requires maintenance. It requires new operator. It requires more training, skill enhancing. So likewise, the operations and number of operations you can suggest to the manager. Okay.
So suppose one scenario, suppose p value should be greater than 0.05.
Yeah,
Okay.
yeah.
Now p value is 0.052. It is came. Is it acceptable?
P value, how much it came?
Now p value should be greater than 0.05.
Yeah.
Now while I'm doing study in Minitab, the p
Uh,
value is came greater than 0.052.
uh,
That means 0.05 greater need to come. I am for me value is came 0.052.
yeah, 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 yeah.
Now can I consider this alpha level is acceptable or not?
Yeah, you can consider. It's the P value should be lower than the alpha. If your P value is lower than your alpha, you reject the null hypothesis. That is the statement which I made. Okay. So whatever, yeah, P value you got, you want to say you got 0.052.
Yes.
So it is
Now I
lower
need to accept alpha
at
null hypothesis.
5% level of significance. Yeah, 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 yeah. You can do it. You accept.
Yes.
Definitely,
Now that
definitely.
2%, how that will be that much differentiate that much condition user. That's what my question is wrong, sir.
No, no, it is not wrong. It is not wrong, but actually, in order to explain it, I need some more time. That is the thing.
Suppose 0.049 is came. Now I can reject null hypothesis.
Yeah, yeah, yeah. So you were telling that how 0.01% is making such a huge difference, right?
Yeah, yeah, same question, sir. But why? Because I already faced this question from, but I don't have that type of answer. Any answer, sir? As per statistics, it is the answer. I don't know anything. Like that, I given solution to the personal.
That
Mm.
is the best you can say. That, sir, as per statistic, this is the conclusion which I have got. Because if you
And
want,
one more.
if you want, I can give you the entire function. I can differentiate it, then I will get that how much change exactly you need to make in alpha to get the entire curve. Everything can be done, but what's the point? Whom you are convincing, that has to be seen.
And one more thing, the manager is telling me, take me 1% alpha, 5% alpha, 10% alpha. How
Yeah.
I can correctly take which percent? That is make me confusion actually.
You provide your results and conclusions for every level of significance. 5%, 10%, 15%, 20% for every particular value, you provide your conclusions. That make a table, make a table and enlist all the conclusions. Thereby, he will also have a better idea in order to visualize your conclusions. Means there is no hard and fast rule that you have to go with 5% level of significance, 10%, 15%, or 20%. These are generally they have been decided. 5% is a very small value. That is why we are telling that initially go with 5% level of significance. But you present the results for almost all up to 5 to 30 you can present. And
No,
try to
actually,
deduce
I
the
can.
statistical inferences that how much level of significance you will increase or decrease that will degrade or improve the quality of product, how much uh, percentage, how much times that you can go for it.
But we can say based on past experience or based on risk of the productivity, we can define maybe that is the alpha value. That means the
Based,
significance level.
yeah, based on the past experiments, you can do it. But if you are doing it for the very first time, like in research, we are doing it for the very first time, we tend to take 5% or 10%, but it is not a hard and fast rule. We can present the results as well as conclusions for almost all significance units. Okay.
So, sir, one more thing, one important thing that is variable distribution. I want to learn, sir.
Oh,
That means which is very important for us. Why? Because we need to do warranty analysis.
oh.
I try to learn that topic, but it is a lot of confusion is given to me.
Variable distribution, the entire topic, it is there in your lectures. If it is there, feel free to go through it once again. Then ask me the doubts in the forthcoming lecture. Why I am telling you that? Because already in great detail I have covered it. So try to go
Yeah,
through the
yeah, yeah.
handouts. Go through the handouts once. Then if it is not clear to you and any confusion is there, then I'll be there in the next class. You ask me. I'll explain it to you separately. Okay. If anything is not clear to you, but you try to go through it once. Exactly at
Got it, sir.
which particular point you are having problem, because gamma function is there, then k value is there, a lot of things are there. First of all, try to explore that how gamma function is defined and how that particular integral we can calculate. Then try to calculate gamma 1, gamma 0. Then after that you come to this particular variable distribution. It will be easy for you to understand.
Actually, in our manufacturing industry,
Mm-hmm.
we will produce per a month this much quantity for this product.
Mm-hmm.
For this product, after running certain kilometers in
Mm-hmm.
field, product is coming out from us
Mm-hmm.
due to some warranty issues. We will note the points and we will calculate the ppm value. And
Mm-hmm.
if ppm is less than 10, 20, we will categorize the issue is seriousness.
Mm-hmm.
Earlier we are doing like that.
Mm-hmm.
Now they want to know what is the prediction future. That means we will get the picture that is called variable distribution. Then they told we
Mm-hmm.
need to do variable distribution.
Mm-hmm.
But our scenarios all are talking in different structure actually.
Okay, okay. That is a particular problem which you have to visualize. First of all, see some of the examples, okay, in this particular field. Try to list down some of the examples. Then, on the basis of those examples, try to formulate your problem. Then you will have an idea that how whether you would be able to apply this particular distribution or not. Means MTTF, mean time to failure only you are trying to predict, right? The
Yeah.
time to failure you are trying to predict, and then you shall be in a position to prepare an envelope and then tell that how much warranty the company should give. on the product,
Yes.
right?
Yes, 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 sir.
So you try to formulate exactly the problem I am not having, so I cannot help you out, but you try to formulate it. Like the problems which we have formulated in the class, you try to formulate it. If some problem is there, then well, but first of all, go through some of the examples of polynomial distribution and then formulate your own problem and try to statistically analyze. That will help you out. Okay.
Yeah, okay, sir.
Okay. Okay. See you soon in the next class. And till then, please revise. And thank you once again for joining the session. Okay. Do join the session next week, same time, same night. Okay. Thank you.
Thank you, sir.